There is a machine that can power an entire house continuously for 50 years without the sun, without the wind, and without a single battery degrading in your basement. It costs less than $50 to build from parts available at any hardware store. It has no solar cells to replace, no lithium chemistry to fail, and no utility company standing between you and your own electricity. It is called a Pico Hydro turbine, and the technology behind it is not new. It has been generating reliable, continuous power since before the light bulb existed. Yet right now, across a country where millions of homeowners are spending tens of thousands of dollars on solar arrays and battery banks that lose capacity every year, almost nobody is talking about this. So, what is it? How does it work? And why has the most reliable off-grid power system ever devised been quietly pushed to the margins? Let's find out. To understand where this technology comes from, you have to go back over 2,000 years. In the ancient world, water was the only energy source that never ran out. Greek engineers were the first to formalize its potential, setting horizontal wheels directly into the current of fast-moving streams, converting the momentum of the water into rotational mechanical work. They were crude by any modern standard, but they established something permanent, that moving water contains kinetic energy, and that energy can be extracted and put to use. The Romans scaled that principle into something extraordinary. At the Bar-Bégal mill complex in what is now southern France, they arranged 16 water wheels in 2 descending rows, each one exploiting the vertical drop of the water to multiply its force far beyond what the current alone could deliver. The height of the drop, what engineers call head, turned out to be just as important as the volume of water passing through. These wheels fed an entire region. The real revolution arrived in the 1870s, not in a laboratory, but in a gold mine in the Sierra Nevada. Mining operations at the time burned entire forests to power their steam engines, while the water wheels they relied on were so inefficient they discarded more than half the energy passing through them. A carpenter named Lester Pelton was watching one of these wheels in operation when something went wrong. The pin holding the wheel to its drive shaft slipped, and a high-pressure jet of water aimed at the center of the buckets struck the rim instead. The wheel, against every expectation, accelerated. What Pelton understood in that moment changed everything. The energy in a jet of water is not just in its weight, it is in its direction. If you redirect that jet as completely as possible, reversing its path rather than simply deflecting it, you extract nearly everything it carries. He designed a bucket with a central ridge that split each incoming jet and turned it back on itself, almost a full 180 degrees. By 1880, his wheel had achieved over 90% efficiency, a figure that modern turbines, after a century of further refinement, have barely surpassed. Within a few years, a British industrialist named William Armstrong had used a single turbine fed by a stream on his estate in Northumberland, England, to power the lights in his home. And for several decades after that, decentralized water power was not an alternative energy source. It was simply how rural life worked. Thousands of farms, small towns, rural mills, and remote homesteads across America and Europe built their own water plants. The technology was widely understood, locally accessible, and remarkably effective. Then came the centralized grid, and with it, the slow, deliberate erasure of everything that came before. To understand why Pico Hydro outperforms everything we are sold today, you first have to understand how it actually works. A Pico Hydro system is defined as any water-powered generation installation producing under 5 kilowatts. What separates it from large dam infrastructure is the approach. Rather than impounding a river, a Pico system diverts a small portion of a flowing stream through what engineers call a run-of-river intake, a structure that pulls water out of the current without blocking it, and returns every drop downstream once the energy has been extracted. The water enters through an intake screen and travels into a settling tank where silt and debris fall out of suspension before the water moves any further into the system. From there, it enters the penstock, a pressurized pipe that carries the flow down toward the powerhouse. This is where the physics become extraordinary. For every 10 feet of vertical drop through that pipe, the pressure at the bottom increases by roughly 4 1/3 pounds per square inch. By the time the water arrives at the bottom, it has traded its elevation for pressure, and that pressure is forced through a narrow nozzle that converts it into a concentrated, high-velocity jet. That jet strikes the precisely curved buckets of a Pelton or turbo runner, spinning a shaft connected to a permanent magnet alternator that begins generating power the instant it turns. The system is not like a solar panel or a wind turbine. There is no intermittency. There is no weather dependency. The stream flows continuously, so the turbine runs continuously, so the power flows continuously, day and night, winter and summer, regardless of cloud cover or season. But this creates a mechanical challenge that separates hydro from every other off-grid energy system. The turbine cannot be throttled. You cannot reduce the flow of a mountain stream the way you ease off a gas pedal. If you restrict flow inside the pipe, you create a pressure surge called a water hammer that can rupture the penstock in seconds. So the turbine always spins at the same speed and always produces the same output, regardless of what the house is drawing at any given moment. The solution to this is an electronic load controller. This device monitors the electrical demand of the building in real time. The moment demand drops, the controller senses the surplus and redirects it instantly to a secondary load, usually a water heating element or a bank of resistors. In a Pico Hydro home, switching off a light does not waste energy. It simply moves that energy into the hot water tank. The turbine stays satisfied. The system stays in balance. And when you look at capacity factor, the comparison with solar becomes almost uncomfortable. A solar panel in most of North America produces its rated output for roughly 4 to 5 hours per day. Across a full year, that works out to a capacity factor of somewhere between 15 and 25%. The panel is doing essentially nothing for the vast majority of the time it sits on the roof. A Pico Hydro turbine, by contrast, runs at a capacity factor above 95%. If you have a 1 kilowatt system, you produce 24 kilowatt hours every single day. To replicate that output from solar, accounting for darkness, cloud cover, and seasonal angle, you would need a 6 kilowatt array plus a significant battery bank just to carry you through the night. A Pico Hydro installation needs no battery bank at all. The stream is the battery, and a mountain stream holding energy as elevation is more reliable and more consistent than any lithium chemistry ever manufactured in a factory. In Nepal, Indonesia, and across rural East Africa, communities that will never see centralized grid power have already built their own micro-hydro systems from locally available materials. They used Pelton wheels, settling tanks, and simple electronic controllers, bypassing the 20th century entirely and moving straight into power ownership. In Australia, researchers have begun recovering energy from pressure normally wasted inside the filtration plumbing of commercial buildings, using miniature turbines to claw back 10% of a building's total energy consumption from water that was already flowing. So why, given nearly 2 centuries of documented performance and a capacity factor that leaves solar completely in the shade, is there not a turbine in every suitable creek in the Appalachians or the Cascades? The answer begins in 1936. The Rural Electrification Act federally subsidized the extension of centralized grid infrastructure into rural America. Before that legislation, if you lived far from a city, you were responsible for your own power. You built a water wheel, or you went without. But when the government began underwriting the cost of running copper wire across hundreds of miles of countryside, the economic case for maintaining your own generation system evaporated almost overnight. Within 2 generations, the knowledge required to install, maintain, and repair a Pelton wheel had largely disappeared from the culture. We traded independence for the convenience of a monthly bill, and the industry collecting that bill had every reason to make the trade feel permanent. Beneath that sits the regulatory layer. The Federal Energy Regulatory Commission asserts jurisdiction over any hydropower installation affecting a navigable waterway. While exemptions exist for very small projects, navigating that framework can still cost a year of processing time and thousands of dollars in environmental review before a single section of pipe goes into the ground. In the eastern states, riparian water law generally allows landowners to make reasonable use of water crossing their property, which makes a run-of-river Pico system largely workable. But in the western states, where the terrain best suited to hydro generation is most concentrated, prior appropriation law treats water as a property right entirely separate from the land beneath it. Diverting a stream through a pipe and returning every drop to the same creek 60 seconds later can still constitute a violation of a water right held upstream by someone else. The system was not built to accommodate energy sources that answer to nobody. And beneath even the regulatory barriers sits the quietest obstacle of all. A well-built Pelton runner, properly installed, can operate for 50 years on nothing more than a fresh set of bearings every decade. There is no recurring revenue in that, no subscription, no service contract, no degrading component engineered to fail on a profitable schedule. The technology is simply too durable to monetize. For those prepared to navigate the paperwork, the starting point is not the equipment, it is the site. You need two things, head and flow. Head is the vertical drop between your intake and your powerhouse. Flow is the volume of water your stream consistently carries. You can measure head with a pressure gauge on a garden hose. You can measure flow with a 5-gallon bucket and a stopwatch. If you cannot reach at least 50 feet of drop and 10 gallons per minute of reliable flow, the economics fail before the design even begins. And critically, you measure flow at its lowest point. Not the spring surge when snowmelt is running hard, not the comfortable autumn average. You measure what the stream carries in August, at the end of summer, after weeks without meaningful rainfall. A system producing reliably through the driest months is worth 10 times more than one built for peak conditions, that falls silent precisely when water scarcity makes electricity most valuable. For those ready to build, the options span a wide range. Complete commercial turbine units are now available that bolt to a concrete pad and wire directly into a standard inverter, offering a straightforward path for those willing to invest in a finished product. For the builder working with a tighter budget, open-source turbine designs have emerged from the off-grid community over the last decade, built around common materials and standard hand tools, allowing anyone to construct a functioning system for around $50 in parts. There is also a lateral approach worth knowing about. A standard centrifugal water pump, the kind sold at agricultural supply stores to push water uphill using electricity, will generate electricity if you run water backward through it. These pumps are mass-produced, mechanically robust, and available everywhere. They are not as efficient as a dedicated runner, but as a proof-of-concept installation on a tight budget, they offer an industrial-grade entry point at a fraction of the price. Whatever path you take, maintain the same discipline. Design for the minimum, not the maximum. Build for the dry season. Size your penstock for the pressures it will actually carry. And check your intake screen after every significant storm, because a blocked screen during high water is the single most common failure point in an otherwise bulletproof system. The Pico Hydro turbine is not a new idea dressed up as a revolution. It is a 200-year-old physical law applied with precision to a problem the modern energy industry has spent decades pretending cannot be solved cheaply. The stream does not send a bill. The runner does not degrade on a schedule designed to generate returns. And the water that powers it was never a product to be manufactured, metered, and resold to the same household twice. A lot of what gets covered in spaces like this was not abandoned because it stopped working. It was sidelined because it was never profitable to sell more than once. If that kind of knowledge matters to you, sharing it is the simplest way to make sure it does not disappear again. And if you want to see how a wall built from nothing more than concrete and glass can eliminate the majority of your heating bill using only the geometry of sunlight and the physics of thermal mass, that breakdown is right here.